In this video, there are two things I want to plug. One is how to draw reference triangles and how to get a reference angle. And the second thing I want to plug is how do you know if your trig functions are positive or negative as far as signs of positive and negative in each quadrant. So first thing I want to pull out here is a reference angle, and a reference angle for all quadrants. Reference angles are always drawn from the terminal side of the angle to the x-axis. That's extremely important. I try to put that as always in the x-axis in capital letters. So we're going to be looking at different reference angles here because we're going to be reflecting triangles across the symmetry of this unit circle. So I've got a pretty busy diagram here, but here's what I've done. What we have studied so far is the yellow triangle, and the yellow triangle represents all the acute angles from anything less than 90 to anything greater than 0. Now we added quadrantal angles, so now we know how to calculate angles of 0. And when we know how to calculate angles of 90. Now we want to be able to calculate angles that are bigger than 90, so we want to get into these obtuse angles. So here's what I did. I created a triangle. The yellow triangle are our acute angles. Now we should be able to use reference triangles to find all the other missing angles in the second, third, and fourth quadrant. So here's what I'm saying. If you know how to find angles in the first quadrant, then you know how to find the angles for all the other quadrants because we can use several ideas of symmetry about the rotation about a circle. So here's the idea. Regardless of what our angle is, I'm going to pull these angles in here just so I have a concept of what they are. These were supposed to be over here, and somehow they all get moved when I go from one screen to the next. But these are just verifications that we have a unit circle that has a radius of 1. I found the length of this red line, it was 0.78. I found the length of the blue line, it was 0.63. If you were to square both of those and square root them, you get a length of 1. So the Pythagorean theorem is satisfied. So what I did is I took this yellow triangle and I reflected across the y-axis. So now on reflections, what we know about reflections is that sizes of angles and side lengths are preserved. So let's get this down to an angle that we're going to be using quite often. Let's go to a 30-degree angle. So we're pretty close to a 30-degree angle right there. Let me get that out of the way. Now, if we know how to find the measure of a 30-degree angle in a unit circle, we said the sine of a 30 is equal to 1/2. And if you see that over here, it's reflected. And the cosine of 30 is the square root of 3 over 2 in the previous video. And if you run that approximation, it is your 0.87. And I should be pointing to the values here. Okay, so now what we're going to do is we're going to find the angles or the sine, cosine, tangents of angles that are bigger than 30, such as a 150-degree angle. If I make this a 150-degree angle, then that is an obtuse angle that we haven't done before. But we're going to use the reference angle. Remember, I started off with the definition. It says go from the terminal side of your angle down to the x-axis, and that will be your reference angle. So if our angle is 150 degrees, then the reference angle here is 30 degrees. That 30-degree angle is the reflection of our original yellow one, which was here. So that means all of the angles and side lengths have to be preserved on that reflection across the y-axis. So I'm going to take that and we'll reflect it over here. So this length is exactly the same as the length of the one on the right. So the only difference is because we're to the left, it's a negative 0.87 as a value for our x-coordinate over here. I'm sorry, x-coordinate up here in our ordered pair. X comma y. X value is a negative 0.87. The other thing that is preserved is the length of this side, which is a 1/2. So this has a length of a 1/2. And since it's upward, it's positive, which is signaling here. So when we do these calculations, what we're going to do is we're going to find the cosine of a 150-degree angle. So we draw an angle of 150 degrees, and we stop. Then we draw our terminal side. Then what we do is we figure the reference angle. The reference angle is always from the terminal side to the x-axis. That's 30 degrees. Then we use our first quadrant 30-degree reference triangle to help us figure these things out. Or at least we can use the 30-degree reference angle to help us figure this out. So we really don't have to know the cosine of 150. What we need to know is the cosine of its reference angle, which is 30. So if we do the cosine of 150, that is the adjacent side, which is a negative square root of 3 over 2. Same value as this, it's just got reflected across the y-axis. The sine of a 150-degree angle would equal the y value, which is the reflection of this side across, but if we reflect across the y-axis, that is equivalent to a half. So that's how we're going to use reference triangles to help us solve angles that are bigger or larger, such as quadrantal or obtuse angles. Just a second, I got to turn off the jet. Okay, so then whenever we have an angle that's in the second quadrant, I'm going to clear up this image just a bit. Whenever we have an angle in the second quadrant, look at the blue triangle and the yellow triangle. Here's what we're going to be looking at as far as referencing. As our angle gets smaller, it doesn't matter, the blue triangle mirrors it completely, so whatever we have in the first quadrant for values, the only difference between the x and the y values in the first quadrant and the x and the y values in the second quadrant is that the x values are the opposite, because we're reflecting the yellow across the blue. So we're going to be able to find any angle in the second quadrant that is bigger than 90, so 90 is less than theta, which is less than 180. That's going to take care of all of our second quadrant angles. Well, anytime we do that, we're going to be measuring our angle theta to here, and that is always going to be a little bit short of theta, or some measure short of 180. So what we do to find our reference angle is always take 180 degrees minus your original angle. In the previous example, I had a 150 degree angle. So what is the reference angle? 180 minus 150. So that was a 30 degree reference angle. If we would select the angle that it is here, this is, we put it at a different angle. Say we put, oh bugger, wish I wouldn't have done that. No harm, no foul here. We'll bring it down just a little bit to center it. If we were to move this angle D up here, and we slide it up, and let's make it a 70 degree angle. So let's say I made that a 70 degree angle. If this is a 70 degree angle as a reference angle here, then what we're looking at then is an angle that goes from here all the way over to here as our obtuse angle. So our obtuse angle is 70 degrees short of 180, which means this has to be a 110 degree angle. So what we do is we take 180 minus our angle for theta that they give us, and we use that as our reference angle. And that's what we're going to use to help us calculate angles in the second quadrant. Now, not only can we go to the second quadrant, but we can go to the third quadrant. So this is taking our yellow triangle, and if we're going to rotate it and make it an obtuse angle, the yellow triangle comes all the way down here into the third quadrant. Okay, so let me come back. If we're going to do a third quadrant angle, it's got to be an angle that is bigger than 180, because that would put it at quadrantial of 180. So we've got to be an angle bigger than 180. So third quadrant angles are going to be angles theta that are greater than 180, but less than 270. So it's all the angles that are going to be pinned in this quadrant. Every angle that we get in there is going to register somewhere between 180 and 270. So if we get an angle that we start off with, let's start off with an angle of 240 degrees. So we rotate an angle of 240 degrees. What we really want to do is we want to figure out what is the reference angle in here. We don't want to work at 240 degree angle, we want to work the reference back to the x-axis. So in this one, we've got to figure out how many degrees past 180 did we go. So we're going to go 240 minus 180, which is going to give us a 60 degree reference angle. So in a unit circle with a 60 degree reference angle, we know that the cosine of a 60 degree angle is the square root of 3 over 2. But because we're to the left, it has to be a negative square root of 3 over 2. Then if we take the sine of a 60 degree angle, using our reference angle, the sine of a 60 degree angle is always equal to positive, or a half, but since we're going down below, it's got to be a negative half. And the ordered pair of angle, or of our point D on the unit circle will be negative x, negative y. So our sine and cosine values are both negative in the third quadrant. I'm not touching tangent right now, I'm just working with those. But anytime you get something in the third quadrant here, here's what we do. We always take the angle that they give us, which is theta, and we subtract 180, because we always want to come back and work ourselves back to the x-axis. How many degrees past 180 did we go? So that's in the third quadrant. We also have to reconcile what happens when we get an angle that is in the fourth quadrant. So the fourth quadrant means I've got an angle that's got to be beyond 270. So it's got to be bigger than 270, but it has to be less than 360, because that'll pin it in this fourth quadrant for our angle. So we're looking at angles that could be the measure of, let's try a 315 degree angle. So 315 puts us somewhere in here. So 315 degrees. So if our angle is 315 degrees, we don't want to work with this angle. We want to work with the reference angle, which means we want to find what is the measurement of this angle sitting right in here. Well, if this is 315, how many degrees short of 360? So the math that we're doing here is we're 360, but we're 315 degrees. We are 45 degrees short of a complete rotation, which means our reference angle is 45. That's what we use, and that's what we call reference angles. Now, this 45-degree angle is the same as the 45-degree angle we had in the first quadrant, except that the yellow triangle gets rotated or reflected about the x-axis. And anytime we reflect across the x-axis, the y values become negative and the x values stay the same. So the x value comma y value combination that we have in the first quadrant is just the opposite sign on y. Now, I didn't articulate that on some of the others, but if I take this one and I flip it across in the second quadrant, it's going to be the opposite x but the same y. And if I either do a 180-degree rotation or if I simply take this one and reflect it across the x-axis, then the x's stay the same and the y's become negative, which is very typical. This is nothing more than knowing the signs of your first, second, and third quadrants. So coming back to this problem, if they ask us, what is the sine of a 315-degree angle? We really don't use the 315-degree angle. We use our reference angle in our reference triangle. So if this is a 45-degree angle, then the opposite is square root of 2 over 2, the adjacent is square root of 2 over 2, and the hypotenuse is 1. So the sine of 315 is a negative square root of 2 over 2. The reason I know it's negative is because it's the y value, it's the opposite side, and it's down. Now if we do the cosine of a 315-degree angle, it's equal to the adjacent side, or the x values of the ordered pair, which is a square root of 2 over 2. But that's positive because we're to the right side. So some of the things we have to do, we have to be able to figure out a reference angle. Hopefully I've described what a reference angle is and how we're going to use that reference angle to calculate angles that are bigger than the acute angles. We're going to use all of these acute angle measurements that we had in the first quadrant. We're going to apply them to reference triangles, which will always give us acute angles to work with. All we got to do is pay attention to the sign. If we're in the second quadrant, the x values are negative, the y values are positive. If it's in the third quadrant, x's and y's are negative. If it's in the fourth quadrant, the x's are positive and the y's are negative. Now that correlates to, if we deal with our new definition of trig functions, we get a pretty simple thing that we can look at on, and I summarize it over here. Whenever we calculate trig ratios, we know that the signs of the trig ratios in each quadrant are going to be different. In the first quadrant, all the trig functions, sine, cosine, tangent, all the reciprocal functions, they will be positive because we're going right and we're going up. Right and up are positive values, so x's and y's are both positive. If we get to the second quadrant, and this is where I got the all students take calculus to help us remember what trig functions are positive and negative in what quadrants. First quadrant, all trig functions are positive. In the second quadrant, the only trig functions that are negative are anything that are related to a sine, so like sine and cosecant. So that's because the x values are negative and the y values are positive. So the only ones that are positive, I think I said that wrong, are that the students stand for sine and they are positive. Everything else in here, cosines and tangents, will be negative. By the time we rotate to the third quadrant, any third quadrant angle, it's going to be a negative x and negative y. Now the only trig function that's going to be positive in the third quadrant is the tangent. And since tangent is related to cotangent, tangent and cotangent. And finally, by the time we get over to the fourth quadrant, I got the word calculus there, and you look at the ordered pairs x, negative, y, because the x's are positive, anything associated with an x, which are cosines, are going to be positive. Anything that's associated with a y is going to be negative, such as sines and tangents. So in this acronym, or in this little saying, all students take calculus, telling you what trig functions are positive in the first quadrant. All of them are. What trig functions are positive in the second quadrant? Only those associated with sine, like sine and cosecant. Which trig functions are positive in the third quadrant? Only things that start with the letter T or that are associated with tangent, so tangent and cotangent. And finally, in the fourth quadrant, the only trig functions that are positive in the fourth quadrant are cosine and secant. So we can use that to help us figure out our quadrantal signs for angles bigger than acute angles. And then the other thing that I summarized here is how you find your reference angles. If you're in the second quadrant, you always take 180 minus the angle that they give you. If you're in the third quadrant, you always take the angle that they give you, subtract 180, figure out how many degrees past 180 you are so that you can find your reference angle. If you're in the fourth quadrant, you're always going to take 360 minus your angle that they give you. So we always want to figure out how many degrees short of a full rotation we are. We always want to be working ourselves back to the x-axis towards 360 and 180. And if you do it in radians, you're just going to use pi and 2 pi instead of 180 and 360. So using the concept of reflections in similar triangles or congruent triangles, we can find the values of trig functions for all angles, not just acute ones. So hopefully that clarifies a few things, and now we're going to get into the actual the problems that they want us to do. A lot of background information, but hopefully that helps.